And hello, welcome everyone to this video. So I think last video we were trying to see, what happens if you use a square wave as an input into this so-called simulated system. Yeah, and I know this is kind of messy. I should put all this into a subsystem of sorts. Definitely, probably. Okay, maybe I'll just do that now. Yeah, I will try to put all of this stuff into a subsystem. Okay, a simulation subsystem, so that if want to use it in future, it's easier. Plus, putting things in simulation subsystems also makes it a lot neater. So let me just do that quickly before moving on to the next steps, which is to analyze the results of what happens if you put a square wave into the system, and what's the Fourier transform look like. Okay, so before we do that, we'll just convert all of this into a sub VI or subsystem. So go to edit, I'm going to go to edit, and I'm going to create a simulation subsystem. Okay, so I've just called it some sort of a simulation reactor, a chemical reactor. Clean up. So it looks like it will have 4 outputs. Okay. So the thing it will give is this fuel unit fuel input, some sort of reaction heat. Oh yeah, reaction heat's an output. Fuel input will be shown as well. And let me just open the subsystem. Okay, reaction heat, fuel input. Okay, what is output A? Oh, yeah, because output is actually linked to the output of the fuel generator input. So let's just take a look at the block diagram here. Open subsystem. Let's go to here. Okay, this should not be named output. It's a fuel input. Then CSTR temperature. There's a numeric here which I can just delete. I don't need to do this numeric thing. Okay. Fuel input is also redundant because I'm just showing the value of what the fuel input is. I'll just take that out. Okay, so CSTR temperature is 1. So I take out this fuel input and remove loose ends. This one is a temperature versus time, so it should go here. And I'll clean up this branch. Okay, reaction heat is always a nice output to give, so I'll just leave it there. Okay. Cancel. Let's go to subsystem 1. We will rename it as dependencies CSTR1. Okay. Let's just call it CSTR1. Random CSTR, continuously stirred tank reactor. Let's call it CSTR1. Okay. I'll make it simple. Okay. So now I have a CSTR1 here. Okay, what are we supposed to do? Yeah, I actually want to test the frequency response of this particular CSTR. Okay, it's just a simulated CSTR, but yeah. What is this? Local variable. Okay. Show error. Okay, there's a number of things I actually need to fix. Okay, let's just debug. If you want to skip this part, by all means, please skip. But I'm just going to do some debugging. Okay, so basically the subsystem has an illegal name. There's a leading trailing white space, so I cannot have spaces over here. Okay, I think I know what it is. So let me open the subsystem. Oh boy. Let me fast forward this, then I'll tell you the summary. Okay, so first thing first, I'm going to fix this local variable thing here, which is not working because I just deleted the fuel input note, the fuel input indicator. This is needed because you need to port it into the local variable. Okay. No, this is not the one. Fuel input. So this will be the fuel input thing I need to put in here. There's a reaction heat. Let's see what else. Has one or more terminals with illegal names. So let's take a look at the terminals. Okay, I think this is the one with the illegal name. Because I don't think you can use brackets in the terminal. Maybe that's why. And last but not least, let me just repaint this to give it a nice icon. Okay, let me see. CSTR. Let me put it CSTR1. And we give a glyph, reactor, no, chemical. No. Okay, what diagram should I use? Oh, yeah, I'll just use any random thing. I'll probably change the glyph later. Okay, hardware. Let's put some random hardware like this. It looks really ugly, but you'll have to do for now. Okay, let's see whether this solves the bug. Yes, it solves the bug. And press play. And this should be 15. Okay, and then you'll have a sine wave frequency. Okay, so I'll just, at least this thing is working now. I'll probably get it on Git later. But yeah, let's see what the signals were. Okay, we have new signals, and I'll be messing around with it. A lot of other signals, but this is the signal file for our square wave. So it will just vary between 13 and 17 over 1000 seconds. And this is the input, which is the fuel, and this is the output, which is the temperature. Of course, we cannot take the first few lines of data because they're like, minus sub-zero temperatures, which is not physical in a sort of reactor, unless it's a cryogenic sort of reactor. But yeah, anyway, let's put this into a file for us to just analyze with MATLAB. So I'm going to open this with LibreOffice Calc. That will take a while. Okay, so this is going to import everything. So I'm just going to save as a CSV file, square wave, input, output, 1 times 10 to the minus 2 Hertz. Let me just save it here in the test data. Use CSV format. Now I'm going to copy the output over as well. Oh, this is not the output. This is the output. So let's open with LibreOffice Calc. Okay, so let's do that. Square wave. Let's go up here. All right. So again, first few bits of data, we actually get rid of it. Okay, let's just have a chart to see where things steady out, as is the usual case, like what I like to do. Okay, so chart is to be inserted, XY, and finish. Alright, so we have a nice square wave plot here. I think things after 100 or 200 seconds will sort of even out. So let's just delete data up to about 200 seconds. Okay, we'll delete data till about 200 seconds. And then we'll just use data after that for the frequency response analysis. Okay. So I'm going to go all the way up. Delete the rows, and I'll just save. And this I will put it into MATLAB. Okay. Alright, so let's put it here. Yeah, this is a... Oh, wait, I already have it here. Okay. So I kind of did double work there. Okay, but that at least shows that it is the same stuff. It works. Let me run MATLAB, and we'll use the square wave as our signal. Then we can do some of the frequency response, just to show you the difference between a square wave and a sine wave. Okay, so square wave is good because you actually you take more than one signal. Okay, you take more than one signal. Okay, so I'll just leave this here. It's kind of redundant, but okay, it works. Okay, so I'm going to put it to a fast Fourier transform. I'm going to compare input and output, of course subtracting the DC gain. So I put it in log plots again, actually. So a lot of this will be noise. But we can actually look at the two strongest signals. Okay, the two strongest signals. Alright, so where's the strongest signal? It is this this part here at 0.001 Hertz. Okay. Oh, shucks, sorry. Yeah, your next strongest signal here, it will be here at 0.03 Hertz. So it's like 0.01 times 3, and every time you have a 0.01 times 1, 0.01 times 3, 0.01 times 5, 0.01 times 7, so on and so forth. Okay, those will be your typical peaks in the square wave. Though if you use it, if you kind of look at it in a non-logarithmic manner, you will see that this is your strongest signal. They call it the fundamental frequency. This is one so-called harmonic, which is it's a multiple of the characteristic frequency. So this is 0.01 Hertz, that's the fundamental. 0.01 times 3 will be, I think, one of the harmonics, if I'm not wrong. So it's 3 times of the base of fundamental harmonic. Okay, so that's what square wave is like, and you can see this is a few times shorter. This peak is actually a few times shorter than this peak over here. Okay, and all of these are the valid signals. So the strongest signal is here. This is the next strongest signal, but you can see that it is quite close to a sine wave. Okay, it's quite close to a sine wave. Okay, if you take a look at this sine wave.csv, okay, it's using the same input, similar input and output. Okay, you see the strongest signal will be here. Strongest signal is here. Okay, it's slightly stronger. It's like, I don't know what, 0.2 dB. This one is like -4 dB. Again at 0.03. As you can see, the Fourier transform is very similar for the square and the sine wave. So actually a square wave, from the Fourier transform perspective, it does look like a relatively okay approximation of a sine wave. Okay, so this one's again almost the same. I hope I'm using the right signals. Yeah. Okay, so yeah, just to give you a final check, let's take a look at the square wave and sine wave CSV. You can see the sine wave actually varies between 15, 16, goes to 17, and then goes back down in a sinusoidal fashion. In the square wave, it just varies between 13 and 17, as you can see here. Hopefully that convinces you that a square wave is actually a somewhat good-ish approximation of a sine wave. And that's the point I'm trying to bring across here, that if you can't use sine waves for some reason, for maybe the controller on your mechanical device isn't working very well, and you can only have two very steady values, then a square wave is more suitable than a sine wave, and it will do just as well. However, you will see the similar problem for this is that for square wave or sine wave for that matter, you're only testing one frequency at a time. So it's a very, very slow process. If you're going to use a lot of time to do frequency response, you might as well test many frequencies at once, which was what we are trying to do. Okay, so I'll just stop now. Next time, then we will we'll try to take a look at summation of signals. I'll run you through the more complete version, because I haven't completed the summation of signals VI the last time. There was some bugs here and there. So yeah, that was problematic. Of course, I took some time off the videos to solve it, but let me walk you through it in the next video. Thanks for watching.